Okay, yeah, I think we can get started. Have 1 extra minute. So our next speaker is Donghoon Kim from Recon Institute in Japan, and he will talk about entanglement scaling in fully connected models.
Yeah. Hello, I'm Donghoon Kim from RIKEN Center for Quantum Computing. It's a great honor for me to introduce our recent work here today. I would like to talk about the quantum complexity and generalized area law in fully connected system. This work was done in collaboration with Dr. Tomotaka Kuwahara at RIKEN, and this is the archive link of this work. So first, I briefly introduce the basic concepts and our motivation. The quantum many-body problems, which involves the interactions between qubits on a lattice, plays an important role in various fields. These interactions are usually described by the K-local Hamiltonian, composed of the local Hamiltonian Hg among up to K particles. The ground state of this Hamiltonian closely approximates the low temperature state of this system, so making an important subject of study. When we divide the system into the two parts, A and B, the ground states can be decomposed using each subsystem's orthonormal basis. Then the entanglement between A and B in this ground state is quantified by the entropy of the coefficients in this decomposition, which is known as the entanglement entropy. And there's an important conjecture related to this. If a local Hamiltonian on a d-dimensional lattice has a constant spectral gap that doesn't depend on the system size, then the entanglement entropy of its ground state is upper bounded by the boundary area between two subsystems. This is called the entanglement area law conjecture. The area law indicates that a state can have less entanglement than expected, so it can be more easily simulated. And this concept serves as a necessary conditions for tensor network simulation. And this conjecture has been fully resolved in 1D system for both short-range and long-range interacting systems. It has been partially proven in 2-dimensional systems under additional conditions. In high dimensions, it remains an open problem, and even a subvolume law has not been proven. As an extremely high-dimensional case, we can consider the Hamiltonian defined on a fully connected graph. So here each edge corresponds to the interaction, so it represents all 12 interacting cases. In fact, this type of interactions is connected to various phenomena across nuclear physics, spin glasses, black hole physics through the following models. And it also has some potential to be applied to the quantum computing and quantum chemistry. At first glance, it may seem that this system has no boundary when divided into the two parts, because all qubits in A and B interact with each other. And since there are so many edges between them, we think this system might have high complexity and large entanglement. However, it has been reported some type of classical simulation, the calculation of the partition function, and classical DMRG simulation are still possible for such fully connected system. And approximating the ground energy by a product state is also possible. So reflecting on this, we can have the following question. Even in a fully connected system, could there be some conditions under which the complexity becomes significantly lower than expected? So we can consider the following as a possible scenario. We first decompose the Hamiltonian into the three parts. Here HA and HB are the interactions within each subsystem, and HAB denotes the interaction between A and B. If this HAB has an effectively small Schumann length, we can think of it as having an effective constant size boundary. So in this case, we may anticipate that it could exhibit small entanglement following some order of Schumann length of HAB, like an area law. But of course, even when considering such a finite Schumann length case, ensuring the ground state entanglement between A and B is small is still a non-trivial issue. This is because the counterexample has already been discovered in a general graph system. As shown in the figure, even if two subsystems are connected by a single edge with a finite Schumann length, there exists a Hamiltonian where entanglement of its ground states can depend on full dimension of the subsystem. So the purpose of this work is to demonstrate in such a small Schumann length or finite Schumann length case the fully connected system can indeed have smaller entanglement than expected. So it can be understood as an attempt to establish the generalized area law and efficient classical description of its ground states. Okay, then now I'll explain our setup and main results. We consider a graph lambda with n vertices, where each vertex corresponds to a qubit with Hilbert space dimension d. And all qubits are connected by the edge of the graph, and this edge represents the interaction hij between the qubit I and qubit j. And the on-site interaction at each qubit is denoted by the hi. The ground state of this Hamiltonian is represented by the omega state, and the entanglement entropy of the ground state between A and B is denoted by the SAB omega. And the discussion employed here can be generalized to the K-local Hamiltonian, but for simplicity, we only focus on the two-local case in this talk. And we denote the interaction between two subsystems A and B as HAB. And this is the collection of all interaction hij between the qubit I in A and qubit j in B, like this. I refer to this as the boundary interaction between A and B. We consider the following assumptions for the Hamiltonian. First, it has a constant global spectral gap delta. And the second condition is that each on-site interaction's norm is upper bounded by order 1 constant G0. And most importantly, as a third condition, we consider the Schmidt decomposition of this boundary interaction as a sum of the tensor products of two operators, HAS and HBS, acting on each subsystem. And here, the HAS and HBS are one local operator, which are the sums of the single-side interactions, and its component's norm is upper bounded by 1. So here, then, the Schmidt coefficients of this decomposition is given by the JS over n, the linearly decaying with the system size n. This dependency on the system size ensures the extensivity of the Hamiltonian. And the total magnitude of the interaction strength, the summation JS, absolute value of JS, is upper bounded by another order 1 constant G1. So if the Schmidt length of this decomposition, the DAB, is finite, then this condition is naturally satisfied. To clarify further, let us examine the following example, the Lipkin-Meshkov Gling model. So in this model, all the spins interact with each other by the XX and YY interaction with a uniform strength JX and JY. And then, in this case, the boundary interaction between A and B can be expressed as the sum of the tensor products of these two operators. So each operator is just a summation of the spin operator on the subsystem in the spin direction X and Y. So you can see that this operator corresponds to the HAS and HBS in the above assumption. So this case corresponds to the Schmidt length 2 case because we have the alpha is equal to X and Y. So it satisfies the above assumption. So like this, the finite Schmidt length case and the Hamiltonian with uniform interactions falls within this framework. And you can think this kind of assumption as a generalized version of the finite Schmidt length case. So it can include the wider wider ranges of cases. In this setup, we prove the following main theorem. The entanglement entropy of the ground state of the Hamiltonian that satisfies the previous assumption is upper bounded by the polynomial in the logarithm of the system size. So it has a polylog upper bound. And the exponent is given by the log 1 over delta order. So this result excludes the possibility that the ground state entanglement in such fully connected systems follows the subvolume law. So it cannot exhibit the sublinear power law scaling with respect to the system size. So it means that describing its ground state requires relatively low complexity than expected. A one open question is whether this result can be further improved. The various numerical results indicate the constant upper bound rather than a polylogarithmic one. So proving or disproving it will be an important open problem. And from the preceding main theorem, we can derive the following corollary. For a given delta, we can find a matrix product state that approximates the ground state in an arbitrary subset X within the lattice lambda, the graph lambda. And the error between the ground state and the MPS is given by the delta times the number of vertices in this subset X. At the same time, the required bond dimension is given by the following form with the exponent log 1 over delta. So for fixed delta, it has a quasi-polynomial bond dimension. And this result can be obtained directly obtained from the bound of the entanglement entropy by considering this graph as a 1D array. And similarly to the previous case, if we can improve the bound of the entanglement entropy to a constant, this bond dimension could also be improved to the polynomial form. So demonstrating this is also a related open problem. Okay, then now I explained our main technique used to prove the main theorem. We utilize the idea of the renormalization group through the product state approximation, which we call the mean-field renormalization group method. As a first step, we partition the entire graph into a single site I and the remainder. We then perform the Schmidt decomposition. Schmidt decomposition on the ground state between these two parts. And here we assume the singular values, lambda s, are arranged in the descending order from 0 to d-1, where d represents the Hilbert space dimension, single site Hilbert space dimension. And our primary interest is in how these singular values are distributed. To investigate this, we consider the following local unitary operator ui acting on the site I. So it doesn't change the state with the largest singular value, the 0 state, while attaching a -1 phase factor to the rest of the states. And then we calculate the energy difference between before and after applying this local unitary operator. Since this ui operator doesn't change the reduced density matrix on each subsystem, so this energy difference entirely depends on the boundary interactions between the single site I and the remainder. So by using our assumption, according to our assumptions, this boundary interaction can be decomposed into the sum of the tensor products of two operators acting on each subsystem, with Schmidt coefficients linearly decaying with the system size. So we can obtain the following upper bound, 1 over n times scale root variance, the product of the variance of two decomposed operators. And then we can use the trade-off inequality between an arbitrary operator's variance and the spectral gap, like this. So we can bound each variance by 1 and n over delta, respectively. So finally, this energy difference is upper bounded by the small number proportional to 1 over scale root n delta. So we call this value as the delta lobe, which denotes the robustness of this energy difference. So this small energy change suggests that since this ui operator only leaves the 0 state invariant, a significant portion of the ground state is concentrated on 0 state. So we can prove that the largest singular value, lambda 0, is quite close to 1, while the remaining singular values are very small. It implies that the reduced density matrix on a single site can be approximated by the pure state within an error of the delta lobe. So we call this 0 state as a mean-field state. And at this stage, we can already obtain the scalar to n upper bound of the entanglement entropy. To further improve this, a renormalization process is required. So as a next step, we group the sites into the multiple blocks. It's consisting of n to the power 1 over 8 sites. So the total number of blocks becomes n to the power of 7 over 8. And then we truncate each block's Hilbert space by projecting only to states close to the mean-field state. So we restrict the Hilbert space to configuration only these sites can differ from the mean-field state. So z equals 0 means that every state in the block is a mean-field state. And z equals 1 means that only one state differs from the mean-field state. So through these projections, we can reduce the originally sub-exponential dimension of the block's Hilbert space to a polynomial size. And then we regard this truncated block as a single linearized QD with this polynomial dimension. And we can prove that this projection preserves the ground state in the adder of the following order, depending on the system size n. Since this adder contains the dependence on the system size, we can see that even we choose G as an order 1 constant, we can obtain 1 over poly n adder. And we apply the same projection to every block, which is denoted as the phi 0 projection operator. And then using this projection operator, we define the projected Hamiltonian on this reduced Hilbert space. Since we now consider each block as a single renormalized QD, we need to redefine the interactions between two renormalized QDs by coarse graining the original interactions. So through complicated calculations, then we can express this projected Hamiltonian in a similar form to the original Hamiltonian. And in this process, we should update the system parameters, the system size, and the single QD Hilbert space dimension, and interaction parameter G0 and G1 by reflecting this kind of coarse graining and the information of the projection, especially the number of G. At the same time, by the previous discussion, we can guarantee that the ground state of this projected Hamiltonian approximates the original ground state in the adder of the 1 over poly n. As a final step, we repeat this renormalization process like this. Then as a result, the total system size decreases quickly in the following form. So this structure says that the S0 should be upper bounded by the order of log n. On the other hand, the dimension of the renormalized QD increases along with the system size n. So starting from an original dimension d, it increases with the system size n, and finally it reaches to the dn to the power of order, the g to the power of S0. So by choosing g as an order 1 constant and using the fact that S0 is upper bounded by the order of log n, we can see that the final Hilbert space dimension becomes exponential polylog n. It means that we can find a state that closely approximates the ground state within this Hilbert space dimension. So it can conclude that entanglement entropy of the ground state can be upper bounded by the polylog n. So this is the core idea of the mean field renormalization group. So first, by using the product state approximation, we obtain the scale root n upper bound of the entanglement entropy. And then by using the renormalization process, we can improve this upper bound to the polylog n. And finally, I summarize my presentation. So we have demonstrated in finite Schumann length conditions, the entanglement entropy of the ground state in fully connected systems is upper bounded by the polylog of the system size. And the main technical achievement is the development of the mean field renormalization group. As a corollary, we can find the matrix product state that approximates the ground state with this above dimension. A major open question is whether it is possible to eliminate this polylogarithmic factor and establish a constant upper bound of the entanglement entropy. So yeah, so it leads to some classical descriptions with the polynomial complexity. And beyond the existence, the finding mean field state and approximated ground state is also, in a polynomial time, is also an interesting open problem. So this is the end of my talk, and thank you for your attention.
Yeah, thanks for the nice talk. I was wondering if you could give some intuition as to how the fully connectedness of the graph actually affects your results. Like, how can one see that if you gradually removed edges until you get a 1D chain, that you should recover the 1D area law for gap systems?
You mean what is the intuition that between the fully connected system and the 1D chain?
Yes, as I interpolate my connectivity from like a 1D chain to a fully connected graph, for instance.
Actually, I cannot find some clear connection between them because usually the 1D area law, we use some approximate ground state projector type of the for the proof of the area law. But in this case, we don't use that kind of idea. So it's quite different from the two concepts, I think.
Here, so you have this 1 over n scaling of the cutting.
Right.
That, 1D you don't need. So that's,
Yeah.
Okay, so thank you for a very nice talk. And so like you mentioned that the entanglement area law in like 2-dimension or higher dimension system is a very famous open question. So like your results is you fully solve this problem or you still have some distance?
Yeah, no, of course not. Okay. So yeah, in 2D or 3D, that problem is still very open. But in this case, I just consider very extreme case. So very high dimensional limit of that kind of dimension. So it is quite part of that high dimensional area law proof.
Okay. So but intuitively, like this is a like infinite dimensional system.
Yeah, right.
So okay.
Yeah.
Understand. Thank you.
Yeah.
Thank you for the nice talk. So this is your result is focused on the condition of finite Schmidt rank of the interaction, right?
Right.
Okay, so could you elaborate a bit on how generic or this condition is for fully connected models, and in particular, does this maybe hold for some of the settings of the Brandau-Haro result?
That's a very good question. And so you mean that if I extend the assumption, then what happens, right? Yeah. Actually, we don't have the specific example except the uniform interactions. We want to find that kind of classes, but yeah, for now, the uniform interactions is that most physical example we have. So yeah, that's my answer. You mean the uniform or finite Schmidt length? I think the entanglement area law doesn't hold in that case. If you remove that finite Schmidt length case, then you can see that this kind of systems has some finite scaling with the system size, the boundary. Then that means that it has some another effect from the system size. So I think the entanglement entropy doesn't hold anymore. Yeah.
Okay, so it's a very nice talk, and I have a question on the step 2.
Step 2, yeah. Okay.
Maybe a silly question. So why you choose a 1/8 and not a 1/6?
Yeah. That's also a very good question. Actually, by using this kind of some grouping, then I can show that some vector of the total system size and the so the important parameter is that when we group this kind of some blocks, then we should consider some coupling between these blocks. And this coupling becomes the order of the total size of the block over n to the power of 1/4. So just by for the convenience, I just choose n to the power of 1/8. So then it leads to this kind of vector.
Okay, so
In the yes,
a little bit arbitrary.
Yeah. You can choose another thing, also.
Okay, and another question is, if it's fully connected, how do you define the area?
Yeah, that's also yeah, that's why I say this part. So yeah, of course. So if you consider the graph structure, we cannot say about some boundary. So that's why we consider this kind of boundary interaction between A and B. Then if this HAB has a finite Schmidt length, the Schmidt length is the most important part of the between two subsystems. So if this HAB has a finite Schmidt length, then maybe we can treat the system has some finite boundary. So that's the starting point of the intuition. Then maybe in this assumption, we can find this kind of similar principle with the area law. That is the intuition.
Thank you.
Yeah, just a technical question. So you also assume that you have a finite energy gap, right?
Right.
At what point did this enter? I kind of missed that step.
Ah. Okay. Here, this point. So at first, using some kind of robustness of the energy difference. But in this case, if I want to obtain some upper bounds, then I should use this kind of trade-off inequality between the variance of the arbitrary operator and the spectral gap.
So the energy gap sort of tells you something about the gap in the Schmidt spectrum, or what's exactly the connection? Because like you're singling out the state 0 as the one with the dominant Schmidt eigenvalue, right?
Right.
Okay.
So to obtain this kind of some small robustness energy difference, then I should use that kind of constant spectrum gap. Yeah.
More questions? Okay. Yeah.
I guess more of a response to an earlier question about how does this relate to the paper of me with Fernando.
Yeah.
This achieves something much stronger, right? We just had some, in our paper, had some weak results about the energy density,
right.
where this is a much stronger control over the state. I just wanted to add that part.
Yeah, thank you very much.
All right, then thanks, Donghoon again.
Yeah, thank you very much.